Hello, I'm Surya and I'm the founder of Argonaut. Argonaut is a modern developer platform that automates deployment of applications and infrastructure to the cloud. We are a Y Combinator backed startup and a member of the Cloud Native Compute Foundation. I've led product and engineering teams at large and small companies in various domains, starting from search ads to electric vehicles to enterprise SaaS. While building Argonaut, I've had the opportunity to talk to hundreds of extremely smart platform and infrastructure engineers in companies of all sizes. Two people startups to teams with hundreds of engineers and everything in between, like Hasura, Twilio, Freshworks, Swiggy, Razorpay, and even Google. I've observed some common patterns in the evolution of infrastructure as companies start up and mature in their journey towards product market fit and scale. Equally importantly, there are the outliers to learn from. There is a fundamental shift in the landscape today compared to what it was even 4 or 5 years ago. I've documented some of these observations from my conversations so that you might find it useful in your journey, especially as an engineer in an early stage startup. I'm Surya, and I'm going to talk about cloud infrastructure at early stage startups. The number of options for hosting, deploying, and managing applications has exploded over the last 2 to 3 years. It has never been an easier time to build software. However, each choice comes with trade-offs and constraints and is suited for a specific set of applications. It only takes one hard constraint like compliance, ecosystem choices, or requirement for low-level control to be violated to mandate a migration. This is a ticking time bomb. This talk is going to be a whirlwind tour of cloud infrastructure landscape with thumb rules that will help you make the right decisions for the org in the long run. Keep in mind that these are thumb rules only and your mileage may vary. We will go over a segmentation of companies by stage, the usual constraints brought on by that stage, and some best practices that might help with decisions about the software stack. Some components of the stack that we are going to touch upon are cloud infrastructure and runtimes, deployment tools, observability, monitoring, and so on. Some things that I will not be touching upon are languages and frameworks, stuff related to business logic, no-code tools, etc. Execution is the lifeblood of startups, and it is essential for tech teams to get this right. The choices made early on in terms of both infrastructure and architecture have an outsized effect on the shape of engineering output for years to come. However, the number of decisions to be made is staggeringly high, and the implications of going down one path versus the other are not immediately obvious. What happens when you do it wrong? You'll probably not sink, but you will be battered. The priority for engineering teams is to ship features that users want. A mature developer workflow accounts for the following factors. The first is external facing business outcomes. Speed at which features are delivered is paramount. The cost is an important factor at every stage from startups to enterprises as well. Compliance, ecosystem, and other distribution constraints imposed by the business model also need to be accounted for from day one. The second is internal facing. Developer experience is the engine that keeps the organization running. Collaboration ease for engineers with ephemeral environments, remote development, etc., lead to increased efficiency. Feature richness of internal tooling with automation built in into features like branch previews, support for various rollout methodologies, multi-region deployments, enable engineers to focus on user features rather than on infrastructure. Thirdly, non-functional requirements in the form of robustness, comprising of automation, observability, and scalability are also going to be very crucial. In startups, where there is always a battle for engineering time, building these supporting capabilities in-house is a multi-year journey. The usual challenges I've seen startups face fall into three buckets. Technical, where there are special requirements. For example, when there is video streaming, various distribution models, for example, when the product is a binary as opposed to a web service is involved. GPU heavy workloads, long running jobs, all of these need specialized treatment. Restrictive industries like government clouds and on-prem deployments. Restrictive industries like government clouds and on-prem deployments also restrict the tool sets available for use. Evolving requirements as the company scales leads to a moving goalpost and is one of the hardest factors to account for when it comes to engineering. Secondly, the talent gap is real and hiring for specialized skills is very hard. Lastly, prioritization of this investment has been a consistent challenge in both my experience and in my conversations with others. Infrastructure is rarely prioritized unless it's a burning issue. This means it is always going to be lagging in capability uh, compared to what is required by the organization. For example, Spotify is well documented to have taken over 2 years to finish migrating their workloads onto Kubernetes. Incidentally, they have spent twice that amount of time building an internal developer platform called Backstage. Backstage is a CNCF sandbox project and is useful for larger organizations to help streamline development operations. Not all companies can afford to put in as much bandwidth behind their internal platform. As you can imagine, requirements of infrastructure varies by stage of the company. Here is a map of what factors end up being important at different stages of the startup. And building without a vision of what is going to come next within the next year or two leads to a lot of unnecessary rework. Having such a list drawn up for your team will help plan investments over a longer horizon. Hopefully, this helps teams navigate with a little less uncertainty. I won't be going into each of these as they're mostly self-explanatory, but the importance of each of these priorities differs based on your specific domain. And in the absence of other information, what you see here serves as a good rule of thumb for what is expected out of an internal platform. Wrong choices can be hard to pinpoint. It is very hard to get to the root cause of why the engineering pace for an organization is slow, or why it takes 1 week to push out a minor change. These are usually handled within an organization through the lens of technical debt or more time spent on engineering hygiene. You might even see prioritization of purely internal cleanup tasks. This is typically a symptom of a systemic problem that is a mix of both process and technical decisions that are suboptimal in the long run. Shipping fast and iterating, essentially execution, is what keeps startups afloat. Choosing the wrong starting point has a long-term impact. Now, the first thing is SDO metrics get impacted. SDO stands for software delivery and operational performance. These are the strongest indicators of technical health of an engineering team. And it is measured by deployment frequency, the lead time for changes from when the code is considered development complete to when it actually reaches a user, time to restore services or MTTR, change failure rate, which is the number of successful deployments, which is the rate, change failure rate, which is the ratio of number of successful deployments to failures. As engineering teams grow, it is important to keep track of these indicators. Long-term engineering debt gets accumulated, and that has a very significant side effect. Poor developer retention is primary among those. Good engineering likes working with other good engineering. Adding headcount, but not improving feature velocity is yet another side effect. Long ship cycles is a third, and this usually leads to large wait times for features to be in production. And this is the cause for a lot of friction between engineering teams and the other teams within the organization. Costly migrations also become necessary, like moving from Heroku to AWS or GCP. It is never pleasant, but it is almost inevitable. Large undertaking to containerize all applications, etc., is another example of a costly migration, where this can be avoided from day one. Elite teams can provision computing resources as needed automatically without any human interaction required on the part of the provider. Engineering team happiness suffers in the absence of a shipping culture. There are a lot of common anti-patterns which will help diagnose and identify the symptoms of an underlying systemic cause. Some of these you would have already seen. An example is logging into VMs directly via SSH to deploy to production, likely using a Git pull, for version control. Images and binaries built locally by developers and pushed to a registry for deployment to a production environment is yet another thing that we commonly see. Databases exposed publicly so that local access is present for engineers to debug is yet another. Hard-coded URLs in the absence of service discovery is one more. So there are a lot of these common anti-patterns that we see, and these have long-term effects in terms of both engineering hygiene as well as failures in the organization. The number of options for deploying applications has exploded over the last 2 to 3 years, and it has never been easier to ship software. And you can even do this for free for a long time now. There are many options here, but broadly, the way I look at it, it can be classified into 4 buckets. The first is application-focused hosting, like Netlify and Vercel. These are primarily meant for front-end or JavaScript-based applications, though it can be stretched a little bit. Fully hosted and managed PaaS like Heroku and Render are great. All-powerful platforms like the public clouds are what every team eventually migrates to because of the richness of the ecosystem built around it and the capabilities. There is also a nascent crop of PaaS on your cloud kind of solution more recently popping up. This has the promise of bringing in the flexibility of the full cloud, but with the better UX and ease of use that a PaaS affords. There are some more factors on deciding the hosting provider. These include deployment runtimes, whether you want to go serverless, based on Kubernetes, virtual machines, bare metal, or even containers as a service. The second is maturity of managed services. Inevitably, code bases need to use databases, queues, caches, event buses, and potentially even batch processing. The third factor here is compatibility and the documentation around this particular platform that is chosen. That includes things like CI/CD, observability integrations, and so on. Let's get to some recommendations. This is from a limited sample and may not be representative of the industry at large. However, the tools in this list are generally safe choices. Keep in mind that there is no one right choice. These recommendations are not targeted at side projects specifically, because there is extreme cost sensitivity there. I will touch upon where it may be applicable, and a lot of these recommendations may still hold, but once again, your mileage may vary. The first big choice is going to be around cloud providers. AWS and GCP are primary contenders here. AWS has a good lead over GCP in my experience, especially when it comes to startups. However, some of the GCP products are technically superior. The difference is usually not noticeable for most use cases, but it is there. AWS has an edge, however, because there is always a person on the other side who is reachable for any issues and even potentially technical advice on infrastructure and on architecture. It flips the other way when there is like a reliance on ML services required because of the maturity of ML services in the GCP platform. Both are very generous with their credits, and it is hard to go wrong with either choice. Some of the other options that require special mention are below, and I will go over the pros and cons of them very quickly. Hetzner or Vultr are very popular VPSs. And if you want to trade off engineering time for cost, these are really great options to go for with as low as 1/3 the price of what an AWS will afford you. DigitalOcean is halfway there, where it optimizes for cost and is a lot more featured in terms of managed services availability. However, I would give it a 2 to 3 year horizon before maturity requirements mandate a move to a full cloud. PaaS offerings are yet another. These optimize very heavily for developer experience at the cost of long-term flexibility. Usually, startups end up moving away from something like a PaaS offering like Heroku or Render after a 2 to 3 year horizon. With AWS, GCP, and even Azure, you're optimizing for flexibility at the cost of developer experience. VPSs, DigitalOcean, PaaS are usually stepping stones before the decision is made to commit to a platform. And this decision usually happens for simple reasons. Lack of availability of cloud managed services like storage buckets, managed queues, etc. being present, even things like a simple way to handle service sprawl. Some companies which are not software centric can survive on these for a really long time. Eventually, a majority of teams outgrows these and shifts to a full cloud. When it comes to deployments, a lot of this is based on the choices made for the infrastructure. When it comes to CI/CD, GitHub is a fairly safe bet. Their pace of innovation has been amazing over the last few years, And they deliver a fully integrated experience, including remote dev like code spaces. GitLab is great and provides really good flexibility for build time and very flexible runners. And this is a very good option if you need to optimize for building cost. Argo CD and Flux deserve special mention here for GitOps. When Kubernetes is being used as the runtime, they add a lot of value in the form of enabling GitOps and hence a very hygienic developer experience. This would need to be done in parallel with a build pipeline though, something like a GitHub or a GitLab. A quick note on runtime capabilities. If we look at Kubernetes versus containers as a service like ECS or Google Cloud Run, Kubernetes ecosystem is real and expansive. That offers a huge benefit in terms of third-party tools and library availability. Higher initial investment is required, but it is way more flexible at scale, especially for collaboration and management. This situation of complexity is somewhat helped by the numerous Kubernetes management tools. And I would highly recommend using one of them if you're starting off with Kubernetes. At the enterprise level, there are Rafe, Rancher, and so on. Octeto and Shiba are really beginner-friendly tools, which can get you going in minutes. If we look at serverless, it's a great solution, and it is extremely low development hassle. It's especially great for low volume. It is especially great for low volume traffic like B2B use cases. However, it might get a little expensive at high scale and volumes. On-prem deployments are also going to be a problem with this unless additional tooling is chosen like Knative, which is cross-platform. Usually, serverless stacks are augmented by other runtimes as it isn't meant for long-running jobs, etc. And specializations mandate other runtimes as well. Infrastructure as code is a paradigm that has taken over the world of late. There's a fairly clear winner here in the form of Terraform. It definitely has the better ecosystem and is the safest choice. However, the contenders here are Pulumi and Crossplane. Both Pulumi and Crossplane are very promising and, in my opinion, have a lot more powerful primitives. Pulumi is great for defining everything in actual code written in Python or Go instead of proprietary HCL, which Terraform uses. The disadvantage, however, is primarily with the developer ecosystem and readily available modules and third-party documentation. If Pulumi is chosen for the stack, there needs to be an investment from an engineering perspective made early on into getting the infrastructure as code story right. Crossplane brings an interesting paradigm of continuous reconciliation of infrastructure and configuration. It also exposes compositions, its version of Terraform modules, which are pretty neat. It leverages Kubernetes heavily and comes with associated overheads. This also requires developer investment for making it work internally. While it is possible to use this infrastructure as code paradigm with VPSs, Heroku, etc., I've actually not come across users of Heroku with Terraform. And in my opinion, the two user bases do not intersect because the value propositions for both of these platforms, both of these paradigms are extremely different. Cost is a big factor. And there are two parts to this. One is optimizing cost, and the second is gaining visibility into spend. Optimizing mechanisms are complicated. Most of the cost savings at scale will come from choosing the right architecture for your product rather than something that can be done purely on the infrastructure side. The right architecture, however, is out of scope for this discussion. Some broad considerations which definitely need to be taken into account, which will probably net you a good benefit as well, are things like leveraging spot instances for non-production environments. This leads to a 60% cheaper compute, and purchasing reserved instances if there is predictability into workloads also helps. The second is automatic cleanups. There are a few nascent tools which are trying to do this, but tagging resources with time to lives and having scripts to clean up these resources periodically is a very good way of ensuring that there are no orphan resources. If you're if there is a large media egress requirement, use CDNs. Those costs can be hard to predict, but can skyrocket very easily without the in the absence of CDN. The visibility into cost is usually very fragmented. Tools exist, but only again for the major clouds. A couple of examples that are worth calling out are QCost, which gives a Kubernetes specific view broken down per application, and InfraCost, which gives a cost estimate per pull request. Now, InfraCost requires one to use the infrastructure as code paradigm so that it can do the processing preemptively. Both of these can be very helpful in getting a control over costs. Developer experience is extremely important. A simple fact of the matter is that every team eventually builds an internal developer platform for application engineers to be self-sufficient. The infrastructure layers are simultaneously complex while requiring mundane upkeep, and it is best kept as a separate function in most organizations. Keep in mind that these internal developer platforms are usually investments that are made when the organization is getting larger and not something teams start off with. The primary reason for this is that it is a significant engineering investment over many years to build this capability in-house. Again, Spotify, for instance, has Backstage. Razorpay has one called DevStack. Netflix has a lot of internal tooling, including Spinnaker plus Conductor. And every large company has one. Razorpay, in fact, has a nice KubeCon talk on how they put in serious effort into making this internal self-serve platform. These teams are dedicated and are usually between 5 to 50 people strong and have significant leverage over engineering outcomes on the long run. Again, this kind of a team starts coming into play once the overall engineering team size is over 100 people in size. Beyond just managing the infrastructure and gluing together the deployment pipelines, the following factors end up becoming essential. For the internal developer platform, abstracting out the infrastructure pieces to just work is more or less a precondition for self-serve for application engineering teams. This includes dealing with complex deployment patterns, which may range from multiple regions and encompass various rollout methodologies. All of these done very seamlessly. Policy enforcement for team access, separation, and compliance is yet another factor. When it comes to Kubernetes development, the biggest pain points are usually around the amount of time it takes to build and manage containers. This big pain point can be mitigated by using hot reloads to reduce and eliminate container build times during the development process. This can save significant amounts of time and effort for engineering teams. When it comes to this, DevSpace is a tool that I slightly prefer over Scaffold. Noteworthy mentions here are telepresence from Ambassador Labs. Remote development is also on the rise, and this can lead to a significant boost in onboarding efficiency for engineering teams. GitHub Codespaces is great, especially if you're on the GitHub ecosystem. Gitpod is great, and Replit is doing amazingly well too. However, keep in mind that all of them need some additional tooling to replicate the development observations in production for certain runtimes like Lambdas, etc. Observability is a very crucial piece of this entire pipeline. I have seen teams that know that their product is down only when a customer complains about it. That is a bad state to be in. It is also very hard to get right. And just taking the decision to implement an observability stack doesn't mean it does the job. The specific events and conditions that test for a product's availability and uptime need to be carefully crafted by the application and infrastructure teams working together. This is some recommendations around these. One of the best solutions for an all-in-one kind of an approach is Datadog, especially when used in combination with PagerDuty. This has been the favorite stack from having talked to a whole bunch of startups. It does not come cheap though. And for that reason, a lot of companies do prefer alternate approaches. The cloud default is preferred by most folks as it is the default and very easy to get started with. The UX sort of sucks compared to a dedicated logging and alerting tool, but it does the job reasonably well. Grafana and Prometheus are quite easy to set up and configure for most runtimes. Using something like an uptime robot or Pingdom will help you with detecting and informing if your endpoints are available. Tracing is another piece that is often overlooked, but this has immense value in both debugging and performance optimization of requests. This gets especially useful when there are multiple services in the system talking to each other. Implement tracing. Preferably maintain OpenTelemetry compatibility. A very easy tool to get started with is Sentry, while Jaeger is a very good option as well. A specific note on ELK stacks, in my experience, it is very heavy and self-hosting requires serious commitment. If you're choosing to go with an ELK stack, I would very highly recommend using the managed service. Focus on security in many companies is an afterthought. It is rather unfortunate that it does take a lot of discipline and effort across the board from day one to get this right. Here are some best practices and helpful tools which will probably put you in the right track, but are in no way exhaustive. The first is have isolated resources for production and non-production environments. Set up multiple accounts within an organization in AWS, for instance. That counts as different projects in the GCP world. Use a secret manager. Please do not share .in files across the board. Doppler is great for an easy start. Vault is a very good option as well, but it is a little more enterprisey. Both support variable separation per environment and are compatible with almost every runtime. Using these reduce a lot of overhead for both engineering teams and change management. Continuous scanning. On the runtime, this can be handled by Sneak fairly well. When it comes to the infrastructure as code, Terraform in particular, Bridge Crew is very useful and it gives you diagnosis about your stack before it is being applied. Claire is very useful for running container scans as well, and it is directly built into ECR, which can be a very convenient option to use. Use private instances only. Please do not keep your databases public. If you're using something like a Mongo, Atlas, Snowflake, etc., please make sure you use peered connections. VPNs are essential, especially when all of these instances, all of these resources are behind private networks. Tailscale and or WireGuard are compatible with a wide range of topologies and is a lot more recent. It does the job really well. OpenVPN is a tried and tested solution with a lot of ecosystem built around it already. Companies in certain industries have specific constraints. Those need to be taken into account from day one when the stacks and the infrastructure are being chosen. Web3 projects, for instance, want multi-cloud enablement from day one, as decentralization is typically a goal for many of these projects. That sort of takes options like Heroku out of the picture. Fintech and healthcare companies have stringent data protection and compliance requirements. I'm seeing an increasing number of space tech startups as well, which fall into a similar category of heavy regulation. Developer tools companies may have distribution constraints. These typically come from how they are packaged, whether the entire thing needs to be in like one binary or one image versus developer tool companies may have distribution constraints, especially when the entire product needs to be bundled into one image or one binary. Enterprise software may require cloud agnostic tool choices to work with customers' on-prem requirements. That means choosing cloud managed services might be a difficult choice, especially if they lead to lock-in. B2B low volume traffic without an on-prem requirement can greatly benefit from serverless. So what does an example stack when all of these recommendations are put together look like? For infra management, using something like Terraform, building on top of AWS with Kubernetes, as it is a fairly robust ecosystem. S3, etc., as managed services are a safe bet. For development, I would recommend using DevSpace, especially in combination with Kubernetes. And when the requirement comes up, using something like a Linkerd service mesh. This is usually something that will come up only after you have of the order of 20 services. Dashboards are usually internal. There are great tools which will be able to help you with these, including some of the internal developer platforms that are ready for use. Observability, Datadog, Prometheus, Grafana, and PagerDuty kind of combination is what I've seen most commonly used. Even though Datadog exists, which can do the entire job, usually there's a Prometheus plus Grafana for dev instances, etc. in use because it gets expensive otherwise. For security, I would recommend using something like a Sneak plus a Bridge Crew. Both of them can get very expensive. So that's something to be kept in mind. Secret management, Doppler, Vault, and Cloud Secret Manager are approximately equivalent. Doppler is great for the user experience. Vault is very enterprisey and very full-featured. Cloud Secret Manager is the default and hence lowest barrier to use. However, it can get very expensive. When it comes to identity, I haven't talked about it much in the previous sections, but using something like using an identity provider is a great idea. Okta, Active Directory, or OAuth are all good choices. CI and CD, GitHub or GitLab with self-hosted runners when it comes to scale is a very safe bet. And Argo CD is what I would recommend you use if the deployment is on top of Kubernetes. So what does the end state look like? The end state for this is essentially an internal developer platform that is built on top of your cloud, ideally available from day one, and is the one place where you can achieve all of these different functions. Deployment of applications and infrastructure, monitoring these infra and applications that have been deployed, in the same view, viewing logs, metrics, etc. at the required granularity, especially broken down by application, broken down by environment and team and other granularities. Managing policy for the entire organization. That includes compliance, access control, and others. Most importantly, this development environment also needs to account for and enable seamless collaboration between the various functions within an organization, including SREs, DevOps engineers, and application engineers. So this is the holy grail, which eventually teams end up building in-house. And it's good to have a view of what the end state looks like as one starts off on this journey, so that all the efforts can be aligned towards this robust end goal. A quick note on Argonaut. Argonaut is essentially built with this end state in mind and intends to be the platform that glues together these myriad tools and supercharge application engineering productivity. Thank you very much. It's been an absolute pleasure. And if you have any questions or if you have any comments about any of these, hit me up at my email or on Twitter. Thank you.